Yeah. Okay. Um, anyway, we were also talking about the greenhouse effect, which is due to greenhouse gases like carbon dioxide, like water vapor. Now, big difference between Venus and Earth is that Venus has, as we said, a very thick atmosphere, 90 times Earth's atmospheric pressure at its surface, almost entirely made of carbon dioxide. It's also got some nitrogen, but it's mostly carbon dioxide. And so it's got a very powerful greenhouse effect. Why isn't Earth like Venus? Because on Earth we have what we call the carbon cycle, which keeps the amount of CO2 in the atmosphere at relatively moderate levels. So the primary source of atmospheric CO2 historically is volcanoes. We're adding to it now, but volcanoes pump gases like water vapor, H2O, carbon dioxide, sulfur dioxide into the atmosphere. On Venus, because it doesn't have a carbon cycle, all the CO2 that volcanoes pump into its atmosphere stays there. And so it's just been building up over time. Earth's volcanoes have released as much or more CO2 over the time span of Earth's history as Venus's volcanoes have. But there's a big difference in that the carbon dioxide on Earth gets mostly safely locked away via the so-called carbon cycle. So the idea is that rainwater and oceans dissolve CO2 out of the atmosphere to form a weak acid solution of carbonic acid, H2CO3. Has any of you ever tasted carbonic acid before? The answer is yes, you have, as a matter of fact. Where have you tasted a solution of carbon dioxide in water? Carbonated beverages. Yeah, carbonated beverages. Carbonated beverages, CO2 dissolved in water. You can dissolve a lot more of it under high pressure. And so before you pop the top on your pop, I pronounce it properly. SODA is pronounced pop, by the way. My wife doesn't realize this being from New York City. But in any case, before you pop the top on your pop or soda, um, there's a lot more CO2 dissolved in it. When you pop it, you release the pressure and it starts coming out of solution, making all the bubbles, making all of the fizz. Similar to the reason why deep sea divers can't just come up right away. It'll kill them because if you go to great depth, then lots of nitrogen gas dissolves in your blood. And if you were to suddenly, because the pressure rises, if you come up too quickly and you reduce that pressure too soon, then nitrogen bubbles start forming in your blood and doing things like blocking blood vessels and so forth. Extremely painful condition called the bends, and it can kill you if it gets bad enough. So don't do that. Not that any of you were planning to. Anyway, um, so carbonation does two things. One, most people find the fizz to be pleasant. I know some people that hate it, but I personally find the fizz to be pleasant. The other thing is, what is it about acids in general? How do they taste, generally speaking? You know? Yeah, they taste sour. Yeah, acids tend to taste sour. Have you ever noticed that if your sody pop goes flat and you try to drink it, it's like too sweet? It's kind of sickly sweet. The reason for that is that after the CO2 is released from it, you don't have the sour taste of the carbonic acid anymore to partly counterbalance the sweetness of all the sugar or artificial sweetener in your beverage. And as a result, it tastes sweeter than it does when it's fully carbonated. That's the reason why flat pop soda is too sweet. That's what it comes down to. Fun with science. Anyway, the CO2 that gets dissolved in rainwater and in the oceans, it's a much weaker solution than in carbonated beverages, but nevertheless, it's H2CO3. It's carbonic acid. It's a component of acid rain. Um, Carbonic acid reacts with surface rocks and dissolved minerals to form carbonate minerals, minerals that incorporate essentially CO2 into their structure. The carbon and oxygen become part of their structure, like calcium carbonate, magnesium carbonate, and so forth. Erosion can then bring that material to the sea, or CO2 that just dissolves directly into the ocean. What was that for? Hey, hey, come back. Now I don't know if is it still sharing? Hope so. I'm going to double check there. Share. Desktop 2. No, I don't want to start the AI companion. Go away. Share. Okay. Anyway, so erosion carries carbonate minerals to the seafloor, ends up there as sediments. Microscopic, I like this word, coccolithophores create calcium carbonate shells. Those are, it says should be that. Oh yeah, that create calcium carbonate shells are important contributors to the biosphere with the process as well. So in other words, most of the CO2 that volcanoes emit on Earth gets scrubbed out by the oceans and by rain and ends up on the seafloors and gets incorporated into carbonate minerals. And that's also within the Earth's on continents and so forth as well. There's carbonate minerals. Now, Earth has plate tectonics, where the Earth's crust and lithosphere, the upper part of the mantle, are fractured into a bunch of plates, and those plates slide around with respect to one another. And there's an important process called subduction, where an ocean plate gets shoved under a continental plate, and that subduction process carries carbonate rocks into a layer called the asthenosphere, a partially molten layer called the asthenosphere. And that can produce ultimately volcanoes near the shoreline. And so around the entire Pacific Ocean, have you ever heard of the Ring of Fire before? Around the entire Pacific Ocean is the Ring of Fire. I don't know if that was named after this Johnny Cash song where you go, I stepped into a burning ring of fire. I like to think that it is. But in any case, things like Mount Fuji in Japan, um, Mount Hood, what's the one near Seattle? What's the volcano near Seattle? Nobody knows the volcano. All of a sudden, I don't know the volcano near Seattle. What's the volcano near Seattle? Somebody tell me the volcano near Seattle. No, it is. That's one that blew up in the same range, but there's a large volcano near Seattle that's very famous. What is it? Mount Rainier, yeah, Mount Rainier. Those are examples of volcanoes formed by this process. There are subduction zones nearby. And so it's a cycle, in other words, because volcanoes then can return CO2 to the atmosphere. But overall, it's kept at a relatively steady level. Sometimes it rises, sometimes it falls by the so-called carbon cycle, which doesn't operate on Venus because it doesn't have plate tectonics, and also it's drier than any Earth desert. Okay, what questions do you have at this point? So this keeps the greenhouse being our friend on Earth, the greenhouse effect being our friend on Earth, where it makes it warm enough for the Earth to be habitable, but not so warm that it becomes like Venus. So the runaway greenhouse effect. Eventually, this is going to happen on Earth long before the sun becomes a red giant. How does this work? On Earth, clouds act as a sort of climatic thermostat. If Earth's temperature were to rise for some reason, then that would increase the amount of ocean evaporation, which would create more clouds. Clouds reflect sunlight back into space before it reaches Earth's surface. And so that would then be expected to cool the Earth back down. That's a negative feedback mechanism where a change happens, the response of the system is other changes that counteract the initial change. But this only works, and that's a characteristic of stable systems. They have negative feedback where If the system changes, other changes happen that tend to push you back to where you were. But that only works up to a point because if enough evaporation occurs, well, water vapor itself is a greenhouse gas, and there's only so much cloud cover you can create. So the greenhouse gas, the greenhouse warming by the water vapor becomes more important than the cooling effect of the clouds. Then we've got positive feedback where a change happens and the system responds in a way that reinforces that change. So in this case, you would get greenhouse warming increases the ocean evaporation, but the water vapor increases the greenhouse warming, which in turn increases the ocean evaporation. So you have a situation that starts to spiral out of control. And furthermore, water molecules in the upper atmosphere are broken up into H and OH, hydrogen and hydroxyl ions, by solar ultraviolet photons. High energy solar UV photons have enough energy to break apart water molecules. The light hydrogen atoms escape into space, and so you can't rebuild the water as a result of that. So you lose water. This is Earth's future, and it apparently already happened on Venus, is what it comes down to. This runaway greenhouse effect may have happened early in the history of Venus, and it will happen on Earth when the sun grows sufficiently bright, and then it'll be curtains for life on Earth, right? Even the cockroaches wouldn't be surviving something like that. So long before the sun becomes a red giant, a runaway greenhouse effect will make Earth into another Venus. It'll be uninhabitable as a result of that. Questions? What questions do you have? I mean, don't be too depressed because, again, as I mentioned last time, it's estimated about 200 million to a billion years from now or so is when this will occur. It's a little bit difficult to calculate exactly where the tipping point lies, but it will eventually happen. One way to prevent it, though, would be to, for example, there's what's called the L1 Lagrangian point in between Earth and the sun, where the effects of orbital motion and the sun's gravity and the Earth's gravity balance one another such that something could stay there, essentially, and not fall towards the Earth and not fall towards the sun either. It's not that the net force on it is zero, it's that the net force is exactly what it takes for it to basically orbit at that distance while keeping up with Earth as it goes around the sun. It's an unstable equilibrium point, and so we do put spacecraft there. And if we do, they have to make corrections so that they stay in the vicinity of that point. But in any case, in principle, you could unfurl a giant space umbrella at the L1 Lagrangian point and cut down the solar radiation enough to keep this from happening to Earth. So maybe maybe the AGI robot descendants will decide to do that at some point. I don't know. In any case, if nobody does that, then Earth will become Venus long before the sun becomes a red giant. So it won't be the sun becoming a red giant that'll wipe out life on Earth. It'll be the runaway greenhouse effect. As I mentioned last time, we know that this happened on Venus, or at least we're confident this happened on Venus, because the water that Venus does have is much richer in deuterium, in heavy hydrogen, than Earth water is. It has a much larger fraction of so-called heavy water, water that has deuterium replacing one or both, in some cases, hydrogen molecules, hydrogen atoms in the water molecule. And deuterium would be lost more slowly by this process than ordinary hydrogen is because deuterium is more massive. And so as a result, it's harder to get it up to escape velocity by this process. And so a smaller fraction of the deuterium leaks into space as a result of this. And if it doesn't leak into space, it can potentially recombine and make another water molecule. And so overall, you lose more ordinary water than you do heavy water by this process of ultraviolet dissociation. And so a planet's water gets enriched in deuterium over time. We can look at the deuterium content of Venusian water, the deuterium content of Earth water, the deuterium content of comets and so forth, water in comets and whatnot. And you can estimate how much water a planet has lost by how much richer in deuterium it is as a result of this process. And the analysis for Venus suggests that it's lost over history at least an Earth's ocean's worth of water. And so it seems that Venus early on was a hotter version of Earth that probably had oceans. It probably had something like a carbon cycle. Even if it didn't have plate tectonics, it would have water to keep the amount of water vapor, CO2 in the atmosphere at more moderate levels. But it's estimated that the sun brightening while it was on the main sequence, after about 1 billion years or so, was bright enough to drive Venus into a runaway greenhouse effect. And so that happened long ago. But probably for the first few 100 million years of Venus's history, it was more like a hothouse version of Earth. It probably had much more moderate temperatures and an active carbon cycle and so forth. The thing is, once this happens, you also start on Earth. What will happen is when the temperature gets high enough, it bakes the carbon dioxide out of the carbonate minerals in the crust, and that CO2 then joins the atmosphere. So all that volcanic CO2 that has been locked away in carbonate minerals on Earth all these years will, on a geologically rapid timescale, become part of the atmosphere. And so Earth will have a thick CO2 atmosphere like Venus does. And so Earth will basically become Venus's twin, so to speak. What questions do you have? I think that's fascinating. It's maybe mildly depressing, but we've got some time. So, all right. So let's kill the sun, or at least let's talk about how the sun will die. Let's talk about the what happens to the sun after it leaves the main sequence because of running out of central hydrogen. So first, a very important point, which is that except for the lowest mass stars, which are fully convective throughout their interiors. So here's 0.2 solar masses, a star like that is fully convective throughout its interior, core to surface. Stars are not very well mixed, so that, like an unstirred campfire, most of their potential fuel, hydrogen instead of wood, is never burned, right? If you have a campfire, what can happen if you don't keep stirring fresh wood into the middle of it is that it can burn the wood out in the center, and the wood past that never gets lit, and so you waste most of the fuel. Principle that can happen with a campfire. Well, that's what stars do. Except for the least massive stars, you either have a situation like we have for the sun, where the core transports energy radiatively and the outer layers are convective. Remember that they convect energy towards the surface. Or in higher mass stars, a bit more massive than the sun and above, the core is convective and the envelope, the outer layers, are radiative, because the higher surface temperatures make their surfaces conditions more like deeper down in our own sun, where you're still in the radiative zone, but their cores are convective because, let's see, what type of hydrogen burning predominates in the sun? What are the two types of hydrogen burning? Big picture. There's the proton-proton chain, and then also the CNO cycle. Which one predominates in the sun? Proton-proton chain. In more massive stars, the CNO cycle dominates, because remember that the CNO cycle is much more temperature dependent than the proton-proton chain is. So if you raise the core temperature, which is what happens if you go to higher and higher masses, the core temperature rises. There's a crossing point where the CNO cycle takes over because it's more temperature sensitive than the proton-proton chain. So high mass stars have convective cores and radiative envelopes. Low mass stars have radiative cores and outer and outer convective zones, and then there's a radiative zone in between. And so in both of those cases, The core is like Vegas. What happens in the core stays in the core for the most part. The material that's being processed in the core, the hydrogen fusing into helium, that helium stays down in the core. It's not mixed into the rest of the star. Except in the very lowest mass stars, where it's convective throughout, and so the whole core is, the whole star is mixed. And so that means in the very lowest mass stars, about less than about 0.3 the sun's mass, all of the hydrogen ends up getting turned into helium because fresh hydrogen keeps getting stirred down into the core where it can fuse into helium. But in the sun, the hydrogen outside the core stays outside the core and never gets burnt for the most part. We'll see that hydrogen fusion starts in a shell surrounding the core eventually, but nevertheless, the hydrogen in the sun's outer layers will never get down in the core in order to fuse. So essentially, the sun is going to waste that fuel, so to speak. It will not fuse. About 90% of the hydrogen it has will never get fused. It only uses about 10% of its hydrogen. And that's roughly true for all stars other than the lowest mass stars. They only burn through about 10% of their hydrogen. They waste most of it. For the high mass stars, it's there's mixing in the core, but not outside of it. So again, this stuff out here, this hydrogen out here, never gets down into the core to be fused. And so the very lowest mass stars have spectacularly long lifetimes for two reasons. One, remember we said in general that low mass stars fuse at a lower rate than high mass stars do, and that more than makes up for the smaller amount of fuel they have to begin with, right? A 10 solar mass star is something like 3,000 times more luminous than the sun on the main sequence. So even though it's got 10 times as much fuel, hydrogen, as the sun, it's burning it like 3,000 times faster, which more than makes up for the extra fuel and makes the 10 solar mass star live a lot shorter lifetime than the sun. It works in the other direction too. You go to lower masses, they live longer than the sun because even though they got less fuel than the sun, they burn it at such a slower rate that it more than makes up for it. But the very lowest mass stars have this other advantage, if you want to call it that, and that is they will burn through all of their hydrogen, not just 10% of their hydrogen. And so that means that you cross that threshold and they live much, much longer than even other low mass stars do, because they're going to eventually burn through all of their hydrogen. They've got like 10 times as much fuel that they otherwise would burn through because of the fact that they're fully mixed like that. What questions do you have? That makes sense? What questions? Can I push the magic button? All right. So eventually the sun will burn through all of its hydrogen in the core. It will run out of hydrogen in the core. We'll go through the details in a bit more detail shortly, but the basic idea is this. Once the core is out of hydrogen, it's no longer got a fusion source to help it maintain the pressure to support itself against gravity. And so as a result of that, gravity starts winning the battle with pressure, and the core contracts as a result. So what's happening to the core's gravitational potential energy as it contracts? Is it increasing gravitational potential energy, or is it losing gravitational potential energy as the core contracts? Which way does it go? It's losing it, right? Because, like if I drop this eraser, is it gaining gravitational potential energy or losing it? It's losing it, right? It's losing gravitational potential energy, converting it into bulk kinetic energy of the eraser that when it hits the floor turns into thermal energy, and sound, which also turns into thermal energy. So as the core contracts, it is losing gravitational potential energy. What does the virial theorem tell us? It's a slow contraction, so it's quasi-equilibrium. That lost gravitational potential energy gets turned into thermal energy, right? And also some additional radiation, but it's heating up. In other words, the core heats up because of this slow contraction. And that heats up the previously non-fusing hydrogen surrounding the core. And so you initiate a thin shell of hydrogen fusion around the now inert helium core. And because of this slow contraction that is heating everything up, the temperature in that thin hydrogen fusing shell is higher than in the core today. And so fusion by the CNO cycle happens in that thin shell much more rapidly than hydrogen is fusing in the core today. And that flood of energy into the star's outer layers causes the outer layers to swell up at the same time that the core is shrinking. And so the star becomes what we call a red giant. So this is first a subgiant and then a red giant. So the next stage in the sun's evolution after it leaves the main sequence is to become first a subgiant and then a red giant. So this figure is actually to scale. In other words, on the left here, we have the sun as a one solar mass main sequence star, like it is today. And to scale, this is the sun as a red giant. So the technical description is sun big, red giant sun really big. So here we blow up the current structure of the sun. We've got the hydrogen burning core, 25% or so of its radius. Here we have the red giant sun and this tiny little region in the center. It's kind of like Earth size, basically, much smaller than the core of the sun today. We've got this degenerate helium core. We'll have a lot more to say about degeneracy pressure when we talk about white dwarfs. So for now, I'm just going to say that degeneracy pressure arises from the Pauli exclusion principle in quantum mechanics and produces much higher pressure at a given temperature than ideal gas pressure would. And again, we'll go into that in much more detail. I think Dr. Trees talks about degeneracy pressure in thermal physics. Is that true? Did y'all in thermal physics did you talk about? What's that? Oh, you didn't do degeneracy pressure? Oh, not yet. Oh, yes, right. You're taking it now. Yeah. But yeah, I think you'll get to it. And in fact, I think he typically talks about white dwarfs. So I'll probably beat him to it, and you'll be like, yeah, we've heard this before. Okay. So you've got a degenerate helium core. It's held up by electron degeneracy pressure rather than it's not ordinary gas pressure anymore. Surrounding that is a thin hydrogen burning shell, and the rest of the star is the non-burning envelope. So when the sun is a red giant, it'll be about an AU across at its maximum size, about the distance from the Earth to the sun now. Now it'll be at the center. So in other words, it'll get, like about halfway out to where the Earth is now. It will definitely swallow Mercury. It's likely to swallow Venus. It probably won't swallow Earth. On the other hand, right, will be incinerated because its luminosity will get up to, at its peak, about 2,000 times or so what it is right now. So yeah, just get roasted here on Earth. But the runaway greenhouse effect, long before that, billions of years earlier, will mean nobody cares. There's nobody around to worry about this. So I heard a joke once. I never remember what jokes I've told you, but I heard this joke once where there's two scientists, and one goes and says to the other scientist, according to my calculations, in about 5 billion years, the sun is going to swell up into a red giant and incinerate the Earth. And the other scientist goes, what did you say? What did you say? The first scientist goes, my calculations show that in about 5 billion years, the sun is going to swell up into a red giant and incinerate the Earth. And the first scientist says, wait, say that again? In about 5 billion years, the sun will swell up into a red giant and incinerate the Earth. And then the first one goes, oh, thank God. I thought you said 5 million years. All right. Questions? Okay, so what's this look like on the HR diagram? Here's the sun there. As we'll see, when the sun is swelling up to become a red giant, it follows a path roughly like this on the HR diagram. And so notice that after a little hook here, it climbs almost vertically on the HR diagram. And at first, it's what we call a subgiant. And then it eventually becomes what we would call a red giant. There's no hard cutoff, like, this is a subgiant, this is a red giant. But in other words, first it's a subgiant, then it's a red giant, because this is a gradual process. And so what is the surface temperature doing as it climbs the red giant branch here? It's decreasing, and that's why it becomes what we call a red giant, because cooler is redder. Okay, now if you actually looked at a red giant, it wouldn't really be like ruby red or anything like that. In fact, it would just be kind of pinkish. The other thing is they're so distended, the atmosphere is so spread out that it wouldn't appear to have a sharp surface like the sun does. You'd be able to see that it's more of a fuzzball if you were close to it. So the temperature is decreasing slowly. The luminosity, on the other hand, is increasing. And roughly speaking here, if you made the approximation that the temperature were staying constant, because it's not decreasing that rapidly compared to luminosity. If the temperature were constant and the luminosity is increasing, what does that tell you about the star's surface area? It's got to be getting bigger, right? Because the luminosity, right? What's the magic formula, right? If we look at the effective temperature, L equals what? L equals 4 pi r squared. 4 pi r squared represents the surface area. That's how many square meters times the luminosity. What's the units of luminosity? Yes, what are the units of luminosity? Watts. So watts, surface area times certain number of square meters times watts per square meter. What tells us watts per square meter? Yeah, sigma Tef to the 4th power, right? 4 pi r squared sigma Tef to the 4th is the luminosity. So if you made the approximation that Tef was staying constant as it climbs the red giant branch, the point representing the sun climbs the red giant branch, well, the only way for L to go up is for R to go up. Well, T is decreasing a bit, but the bigger effect is the increase in surface area. That's the primary driver, if you will, of the increase in luminosity. And in fact, the decrease in surface area would be by itself, the decrease in temperature. The decrease in temperature by itself would be reducing the luminosity. So the increased surface area has to be more than compensating for that to account for the fact that the luminosity is increasing. So, right, you should be able to make that argument that the path it's taking on the HR diagram implies that it is swelling up in size. So here's our main sequence star. Here's again our red giant star. And the tiny core and shell are not drawn to scale in the schematic drawing, but you've got a non-burning degenerate helium core surrounded by a hydrogen-burning shell, surrounded by a non-burning hydrogen envelope. Of course, there's helium there too, but it's the usual composition, right? More like 70-28 versus in terms of the mass fractions, whereas the core is almost entirely helium at that point. And you got a hydrogen burning shell surrounding it. What's that hydrogen burning into? Hydrogen is fusing to form helium, and that helium is settling onto the core, increasing its mass, strengthening the gravity in the core, aiding in this contraction process. So the core, the helium ash from the shell dropping on the core is enhancing this contraction and heating and increasing the rate of fusion in that surrounding shell. And again, be sure you realize that fundamental to this is the fact that there's still hydrogen outside the core to be fused, to form this hydrogen fusion shell. And that's why stars become giants. It's because they can go through these shell fusion phases surrounding an inert core, where the shell's at a very high temperature because of the contraction of the core heating everything around it up. That's why it goes through a giant phase. The very lowest mass stars, less than about 0.3 solar masses that are fully convective, never become giants. It'll never become a giant. It just slowly turns itself into a helium, eventually white dwarf, by fusing through all of its hydrogen. It never goes through a shell burning phase that produces a giant like this. Okay, what questions do you have? All right. So this is showing this idea of everything's feeding back on itself, so we can kind of jump in here. It's a positive feedback loop here. The more compact and luminous the energy producing shell becomes, the more the outer parts of the star swell, because all that energy is increasing pressure in the outer parts of the shell. So notice in the central regions, gravity's winning the battle and things are shrinking. But in the outer regions, all the energy produced by the hydrogen fusing shell means pressure is winning the battle in the outer regions. And so the outer layers are expanding at the same time that the core is shrinking. Core growth and rapid hydrogen burning feed off each other in a red giant star, causing it to move more and more rapidly up the so-called red giant branch. And so we'll just jump in here. Stronger gravity, which leads to greater weight of the overlying layers, which leads to higher pressure on the hydrogen burning shell, which leads to faster nuclear burning, which leads to faster conversion of hydrogen into helium, which leads to faster growth of the helium core mass, which leads to a smaller, more massive degenerate helium core, which leads to stronger gravity, which leads to greater weight of overlying layers, which leads to higher pressure. Right? So just building on itself. And so, in fact, if you were watching a movie, the point representing the sun in this time-lapse movie is like 100 million years, right? But would be moving faster and faster up the red giant branch as you go, if you made it into like a time-lapse movie. Note that the outer layers above the core literally are weighing more and more as the core shrinks, because the surface gravity of the core depends on its mass and its radius. If you were to magically shrink the Earth to half its radius, keep everything else, keep its mass the same, but you somehow magically shrunk the Earth to half its current radius, what would happen to your weight as a result of that? It would increase by how much? We can say precisely, by what factor would it increase? Not double. So we shrunk it by half. It becomes half as large, right? So the acceleration due to gravity, if I've got radius r, mass m, what's the acceleration due to gravity at the surface of that? It's g what? Big G. Yeah, it's ultimately over r squared. What's the thing I'm missing here? M, yeah, gm over r squared, right? Because the gravitational force, if I had a little test mass up here of mass little m, gravitational force is g times blah, 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 what? G. So the force on little m due to big M is, yeah, big M times little m over r squared, right? So the acceleration due to gravity, little g, is g big M over r squared, right? So if you shrunk the Earth so that its radius was half what it is now, but it still had the same mass, the acceleration due to gravity would be how many times bigger? 4 times bigger, 2 squared times bigger, right? So as the core contracts, you're adding mass to it, which is also helping the process, but the shrinking radius is also increasing the gravitational acceleration at its surface. And so literally stuff at the surface of the core weighs more as the core shrinks. Even if you weren't adding any mass to it, just the shrinkage would cause everything to weigh more. So the shell fusion has to be rapid because you have to have enough pressure to support all that weight that is increasing as the core shrinks. So the fusion rate has to keep going up to maintain any sort of quasi-equilibrium because you're supporting more and more weight above you, not necessarily more and more material above you, but more weight above you because as it shrinks, the gravitational acceleration of the surface keeps increasing. Questions? Can I push the magic button? Okay. So here's a schematic diagram of the evolution of a one solar mass star. And so right now we have climbed the red giant branch. Later we will talk about, well, the last step in the red giant evolution is what we call the helium core flash. But there's a bunch of points labeled on here. This is a figure from your book with a bunch of points labeled on it. So here's the zero age main sequence. And here is a point labeled 3 where hydrogen in the core is exhausted, core contraction with hydrogen shell burning. We're on the subgiant branch. And then there's what's going to be called the first dredge up. We'll talk about all that in more detail in the next slide. Fortunately, it's all written out in that thing that I handed to you. So, you don't necessarily have to write this all down unless you would like to. You're certainly welcome to. So let's go through all of that. So point 3 there, oops, point 3, right here. And this is according to a particular computer model of stellar evolution for a solar mass star. Point 3 happens 9.8 times 10 to the 9th years after the zero age main sequence, 9.8 billion years after the zero age main sequence. Central hydrogen is completely depleted. Proton chain in the core stops, but the core temperature is high enough that hydrogen shell burning is ignited. Gee, does this track with the idea that, a star with the sun's mass spends about 10 billion years on the main sequence? Yes, 9.8 billion years after the ZAMS is when, in this model, the central hydrogen is completely depleted. So when the hydrogen fusion stops, the luminosity of the core becomes 0 because it's the conversion of hydrogen into helium that is producing the luminosity in the core. And remember that in a radiative zone, the temperature gradient equation was -3 over 4 AC kappa bar rho over T cubed L sub r over 4 pi r squared. And remember that L sub r is the amount of luminosity generated interior to radius r, right? L sub r was the luminosity generated interior to radius r. We've shut down the nuclear reactions, and so it's not generating any luminosity anymore. Now, the gravitational contraction produces some luminosity, but not nearly as much as the nuclear reactions would. So we can essentially say that the core is no longer producing luminosity. So therefore, that equation says dTdr is 0 because L sub r is 0 within the core. Therefore, dTdr is 0. And if the derivative of a function is 0, what can we say about that function? Yt has to be constant as a result of that. So the core is isothermal. The temperature within the core is constant. Unlike in the core today, where it keeps increasing towards the center, when you shut off the hydrogen fusion, the core becomes isothermal, constant temperature. Questions at this point? What questions do you have? So then we get to point 4, right there, point 4, which is 11.39 times 10 to the 9th years after the ZAM. So 11.4 billion years is the age of the sun, if you count it as starting at 0 when it hit the ZAMs at this point. So helium added to the core by hydrogen shell burning causes its mass to exceed the maximum possible mass of an isothermal core, which is called the Schoenberg Chandrasekhar. Chandrasekhar. That's she can't correct my pronunciation. Limit from 1942 is when they came up with this. And there's a rough derivation of this in the text. I'm not going to go through it here. So it says that the mass of an isothermal core divided by the total mass of the star, the maximum mass, I should say, of an isothermal core divided by the total mass of the star is about 0.37 times the mean molecular weight of the envelope, the stuff outside the core. So we say everything outside the core is the envelope because it encloses the core like an envelope encloses the letter, over the mean molecular weight of the isothermal core squared. Again, you can look in the book for a rough derivation of this relationship. So as an example, the sun's got an initial composition of hydrogen mass fraction of 0.708, helium mass fraction of 0.272, metallicity of 0.02. That's about right from the sun. And the envelope hasn't had anything from the core being stirred up into it. So the envelope maintains that composition that the sun was born with. So if you plug those numbers in and calculate the mean molecular weight, you get about 0.61 for the envelope. The mean mass per particle is 0.61, the mass of hydrogen atom. For the core, at this point, it's pure ionized helium. And remember that we estimated that the mean molecular weight for pure ionized helium is about 1.34. Plug that in and you get that the maximum mass the isothermal core could have would be 0.08 solar masses. Partial degeneracy in the core means that actually the real result is more like 13% of the star's mass can be within the isothermal core. When this limit is reached, that's what's defined to be the end of the main sequence life for stars less than 1.2 solar masses. The core starts to collapse on the Kelvin-Helmholtz timescale. So when I teach astronomy 111, I say that the main sequence is when the star's fusing hydrogen in the core. And then when it runs out of core hydrogen, it's not in the main sequence anymore. We see this technical definition says, no, it's actually fusing in a shell for a while and not within the core. And it's still being said to be on the main sequence until you get to this limit. And then the core starts to collapse, to contract more rapidly. And that really kicks things into higher gear in terms of the envelope starting to expand. And so that's really defined to be the end of the main sequence time. It is a definition, though. You could also define it as when the core runs out of central hydrogen. But if you base it on what's going to happen to the outer layers of the star, when they're going to start significantly swelling up, it's when this limit is reached. What questions do you have? So remember that the Kelvin-Helmholtz timescale, that's the one where you estimate from gravity powering, for example, how long could the sun maintain its current luminosity from gravity power, from slow gravitational contraction. In other words, what we're talking about here is the core is now starting to produce a significant amount of energy from gravitational contraction, whereas before that, degeneracy pressure and ideal gas law pressure combined within the core was keeping it from shrinking much. So things pick up when the core starts to be able to contract more quickly. So the core temperature increases by the virial theorem, heating up the hydrogen burning shell, causing the luminosity to increase and the envelope to expand and cool. And so if you look again at point 4 there in this, it's kind of this inflection point where now we're going to start climbing more. So we're at point 4. At point 5, 11.64 billion years after the ZAMs, the H- ion, which we've met before, dominates the envelope opacity. And it turns out that produces deep convection. The outer layers become convective deep down towards the core. And it turns out that a convective star is inhibited from continuing to lower its surface temperature and moving to the right in the HR diagram, and instead starts climbing upwards, like we see climbing the red giant branch. That's called the Hayashi track, after the Japanese astronomer who deduced its existence. Protostars descend along the Hayashi track when they become deeply convective, and a post-main sequence star climbs the Hayashi track when it becomes deeply convective. And so that's why, if you look back at the pre-main sequence evolution of the sun, it looks like it's descending on pretty much the same track on the HR diagram that it's climbing now. And so this is when it's on the red giant branch. And look at the time scales here, right? In other words, it goes to go from 0.3 to 0.4. Look at that. It was 9.8 billion years to 11.39 billion years, right? So quite a still, like about 6 billion years or something like that is how long that took, right? To go, stop it, to go from 3 to 4, and then 4 to 5 was much shorter, right? We went 11.39 billion years to 11.64 billion years. So things are picking up. The point representing the sun is moving faster on the HR diagram at this point. Break time. Okay, so um, 0.6, 12.27 billion years after the zero age main sequence, that's when the core reaches the temperature of 100 million Kelvin. And that's the ignition point of the triple alpha reaction that converts helium-4 into carbon-12. But in a low mass star like the sun, where the core is degenerate at the initiation of the helium flash, it happens explosively. At the ignition of helium burning, it happens explosively in what we call the helium flash. And soon we'll discover that we have to say that in a certain special way. Some of you may already know this certain special way. But I will mention that, again, electron degeneracy pressure, it's a quantum mechanical phenomenon due to the exclusion principle that causes particles such as electrons or whatever it is that's exerting the degeneracy pressure to have much higher kinetic energies than they would if it was just an ideal gas. It's again, we'll talk about it in much more detail. The basic idea is, remember that the Pauli exclusion principle says that two fermions, two particles with half integer spin, cannot are the maximum that can occupy any given spatial orbital wave function. And that's responsible for the periodic table, right? In other words, without that, in every atom, all the electrons could just be in the 1s orbital, the ground state orbital. It's the Pauli exclusion principle that is the reason why they can't, why they have to go into higher and higher energy orbitals, and not just be in the ground state. And it applies not just to atomic orbitals, it applies to particles in a gas. And so in the core of the star, essentially what happens is that the electrons are forced into high energy orbits where they have much more energy than they would according to classical thermodynamics. But I don't want, again, we'll talk about that in much more detail when we talk about white dwarfs and neutron stars and so forth. But for now, just think of it as this quantum mechanical phenomenon that produces much higher pressure than the ideal gas would, the ideal gas law would. In fact, when we talk about white dwarfs, for example, we'll see that a white dwarf is a final stalemate in the battle between gravity and pressure, and electron degeneracy pressure would be able to support the white dwarf even down to 0 Kelvin. It doesn't need to be hot. They're hot because they're leftover cores of stars, but they'll eventually cool down into what we call black dwarfs. With enough time, they'll get closer and closer to 0 Kelvin, but they'll still be stable because degeneracy pressure doesn't require non-zero temperature in order to be significant, because you can't put all the particles in the ground state. They're forced into high energy states, even at low temperatures. So the pressure is much higher than the ideal gas law would imply, because the ideal gas law would imply everything stops moving as the temperature approaches zero. Not so in quantum mechanics because of the Pauli exclusion principle. But I do want to point out that it sounds very exotic, and it is in some level. But on the other hand, you've experienced electron degeneracy pressure before. It's the reason why metals are so stiff. The electrons are moving, well, they have energies, which if you turn them into classical speeds, in a metal, the equivalent temperature that produces the same pressure for the electron gas that you would expect from the ideal gas law is only of like 100,000 Kelvin. The electrons are, quote unquote, moving as fast as they would classically if the temperature was 100,000 Kelvin. But quantum mechanically, you don't need that. And so the metal is stiff because of the degeneracy pressure exerted by its electrons. The stiffness of a metal is an everyday example of electron degeneracy pressure. And that's what's supporting the core of a low mass star while it's a red giant. So in other words, here we've got our red giant. The weight of the overlying layers of the star is supported by degeneracy pressure of the sea, if you will, of tightly packed electrons in our electron degenerate helium core, surrounded by the hydrogen burning shell, surrounded by the non-burning envelope. The core is around the side of the planet Earth, which is very small in terms of a star. So it's this tiny region in the center of the star, the core, which is being supported by electron degeneracy pressure, and the hydrogen burning shell, again, is this tiny region in the middle of the star. So here's a zoom in, so to speak. You've got a degenerate electron sea, and the helium nuclei formed from hydrogen fusion while the core was on the main sequence. The helium nuclei are free to move about within the electron sea, acting like a normal gas within the degenerate electron gas. So the electron gas is producing almost all the pressure. That electron degeneracy pressure is much stronger than the ordinary gas pressure of the helium nuclei within the core. So it's electron degeneracy pressure that supports the weight of the core, or the weight of the star. And a very important thing about electron degeneracy pressure is it's almost completely independent of temperature. Most of the kinetic energies of the particles are due to the Pauli exclusion principle, due to them being forced to be in higher energy orbitals by the Pauli exclusion principle. The lower energy orbitals are already occupied. And so as a result of that, the temperature hardly has any effect on degeneracy pressure until the temperature becomes so high that you give enough energy to the particles to start behaving like an ordinary gas again. So to a good approximation, electron degeneracy pressure is independent of temperature, and that's crucial in explaining why helium burning begins explosively in a low mass star with a degenerate core. So first of all, how does helium burning proceed? It's called the triple alpha process, because an old name for, well, a current name still, but in the old, when radioactivity was first being studied, and they didn't know what it was, they classified kind of, three major types of radioactive decays. And so they talked about alpha rays, beta rays, and gamma rays, depending on how they interacted with other matter. Well, now, of course, we know that what they were calling gamma rays are what type of phenomenon? What is a gamma ray? It is a high energy photon, right? So we still call them gamma rays. Do you know what beta rays are? They're electrons or positrons. So they are produced when a nucleus has either a proton turn into a neutron by emitting a positron and a neutrino, or and that's called beta plus decay because it's emitting a positron, or a beta minus decay is when a neutron turns into a proton by emitting an electron and an antineutrino. So those, again, were called beta decay before we knew what was going on, and now we know that beta particles are electrons or positrons. What they were calling beta particles, beta rays, are electrons or positrons produced by nuclei that are having either a neutron turn into a proton or a proton turn into a neutron. So we talk about beta plus decay, beta minus decay. And then alpha rays, we now know, are helium-4 nuclei spat out by unstable nuclei. The helium-4 nucleus, that combination of nucleons, is very stable. And so unstable nuclei often decay by spitting out a helium-4 nucleus, an alpha particle, quote unquote. And so because helium-4 nuclei are called alpha particles based on the relationship to radioactive decay, the triple alpha process refers to the fact that three helium-4 nuclei fuse to form a carbon-12 nucleus in 2 steps. First, 2 helium-4 nuclei fuse to form beryllium-8, but beryllium-8 is an unstable nucleus. Turns out there's no stable nucleus that has 8 total particles in it. It just doesn't exist. There's no stable 8 nucleon nucleus. And so that beryllium nucleus will very quickly just fall apart again back into 2 helium-4 nuclei, unless in the nick of time another helium-4 nucleus comes along and collides with the beryllium-8 before it breaks apart and fuses with it to form a carbon-12 nucleus. And so the energy released is carried off both by the motion of the carbon-12 nucleus and by a gamma ray. That's the result. So ultimately, 3 helium-4s, 3 alpha particles, triple alpha, fuse to form a carbon-12 nucleus. And so that's the next stage in fusion in the sun, is that when its core gets hot enough, it will start fusing helium into carbon. And that's as far as the sun's going to get in terms of major fusion stages. It will never get hot enough in its core to fuse carbon into anything else. But more massive stars with enough mass, do fuse carbon into, I think it's magnesium, if I'm not mistaken, I forget. But anyway, this is the end of the line for the sun in terms of major fusion reactions. The helium fusion is the last fusion reaction, major fusion reaction in a low mass star like the sun. So the helium core left over from when it was on the main sequence fusing hydrogen helium, for a while it's inert. It's not hot enough for the triple alpha process to occur. But again, the core keeps having helium added to it by the hydrogen fusing shell. Its mass keeps increasing. It contracts. It keeps heating up. And when it gets to about 100 million Kelvin, that's where the nuclei are moving fast enough to start fusing with one another in the triple alpha process, forming carbon-12. And some oxygen-16 also gets formed. How do you think you get some oxygen-16 out of this as well? How would you get oxygen-16 out of carbon-12 in a core full of helium? What's that? Yeah, if you add helium-4 to carbon, oh God, well, I just bumped it, I think. Stop being so touchy. Okay, still says I'm screen sharing, so I'm just going to assume I am. Okay, yeah, if you add 2 protons and 2 neutrons to carbon-12, how many protons do you have? Well, how many protons in carbon-12? Well, that's the total number of particles. 6, yeah, all carbon has 6 protons. How many neutrons? 6. If I add a helium-4 to that, I get a nucleus which has how many protons? 8. How many neutrons? And what do you think we call that isotope? Oxygen-16. Yeah, so you get some oxygen-16 as well, because you get some additional fusion of helium with carbon-12. But it mostly makes carbon-12. But we do say that the sun will leave behind a carbon-oxygen white dwarf, because you also get some oxygen-16 out of helium fusion. Okay, any questions at this point? But This happens explosively initially. It starts out explosively. Why? Because the solar thermostat isn't working in a degenerate core. So the sun, good news, is never going to blow up like a bomb. If there's one thing that'll ruin your day, it's having your star explode as a bomb. Why won't the sun explode as a bomb? Because of the so-called solar thermostat, if you will, which works like this. So we know that in the sun's core, in general, right? Today, there is almost perfectly a balance between what two forces, right? Repetition is the key to learning. The inward force of gravity and the outward force of pressure, right? The outward push of pressure, it's really a pressure gradient, right? The pressure is decreasing as you go out so that on any layer, there's a net outward pressure force. Gravity and pressure are essentially in balance with one another. Let's just suppose for some reason that the core temperature were to rise a little bit. What would that do to the rate of the nuclear reactions in the core? I mean, it's up there, but just think, right? Nuclear reactions go faster as the temperature rises, right? Roughly T to the fourth power in the sun's core is how the nuclear reaction rate goes with the proton-proton chain at near solar core temperatures. So a slight rise in core temperature for whatever reason would lead to a large increase in the fusion rate because fusion is very temperature dependent. So a little rise in temperature would greatly increase the fusion rate. What would that do to the pressure? It would raise the pressure, right? Which would tend to cause the core to expand. And if you expand, you are converting thermal energy into gravitational energy instead of the other way around. An expanding core is converting thermal energy into gravitational potential energy. So the core expands and cools down, and you're back to normal again. Hooray! It's what kind of feedback is this? Is this positive feedback or negative feedback? This is negative feedback where a change in the system naturally induces a response that tends to take you back to equilibrium. So that's what does a thermostat do? If you have a thermostat, and usually it's either set to turn on the heater or turn on the air conditioner, but you can have a thermostat where, okay, I set the thermostat such that I want my room to be, let's say, 70 degrees Fahrenheit. If the temperature gets to 71 degrees, let's say it's set this way. If the temperature in the room gets to 71 degrees, what's it do? It turns on the air conditioner and cools the room back down again. And if the temperature falls to 69 degrees Fahrenheit, let's say it wants to be plus or minus a degree Fahrenheit, temperature falls to 69, it turns on the heater, right? The furnace. And so you keep the temperature in a narrow range. It's a thermostat. That's what a thermostat does, right? Negative feedback. If the temperature rises, it kicks on the AC. If the temperature falls, it kicks on the heater. This is similar. If the temperature rises, it kicks on the AC, so to speak. It makes the core expand, cool things back down, and return to normal again. And it'll go the other way too. If for some reason there's a slight drop in temperature, that'll lead to a larger drop in the fusion rate. Well, now gravity is going to start winning, core contracts, heats up, restores things to normal again. So this is why the sun and other stars, when they're on the main sequence, don't blow up like a bomb because of this fact, because of this feedback like that. Make sense? What questions do you have? Okay. But now let's consider the degenerate helium core when helium fusion begins. The thermostat is broken because notice crucial here was that the fusion releases energy that raises the core pressure that causes it to expand and equilibrate, so to speak, equilibrate, okay? But now consider helium fusion begins in the degenerate core, and so that heats up the core and it's degenerate So what happens to the core pressure as a result of that increase in temperature? What did we say about degeneracy pressure? Does degeneracy pressure depend on the temperature? Essentially, no. Essentially, no. It's a little bit, but for all intents and purposes, it's just independent of the temperature. So nuclear reactions begin converting helium into carbon. So the core heats up and the pressure says, so. And so it can't expand. It can't, that energy being released can't go into expanding the core. It all goes into increasing the temperature. So the fusion begins, the temperature rises as a result. What does that do to the nuclear reaction rate? Makes it go faster. So the core gets even hotter. Can it expand? No. So what happens to the nuclear reaction rate? Even faster. And so positive feedback, it goes out of control. The nuclear reactions begin, which makes it hotter, which makes the reactions faster, which makes it hotter, which makes the reactions faster, boom! It goes out of control. And this gives us the so-called helium flash. Exactly, exactly. Yes. Why did Anushka say, ah? Some of you already know, because we must be trained to, whenever I say helium flash from now on, you have to say, ah, in response. Why? Well, when I was growing up, my favorite band was Queen. Um, I mean, come on, they could sing. Brian May, he had a bachelor's degree in physics when he was in, at the time when they were at the peak of their popularity. And then he decided, because when Brian May, the guitarist, was young, he had a choice to make. He could either become an astrophysicist or try to go to become a famous rock star. And well, that's because he was really smart and he could also play guitar very well. And I think if I were in his shoes, I'd probably do the rock star route as well. He has this unique ability to play the guitar. Queen's very educated band, so their bass guitarist has a degree in electrical engineering, and he actually designed the uh, the electronic device that gave Brian May's guitar its unique kind of medieval sound. Um, so then later, when Queen was no longer so active, Brian May said, "Yeah, but I still want like to do the astrophysics thing." So he decided to go and finish his PhD. So now he's Dr. Brian May. I think he's actually Sir Dr. Brian May, as a matter of fact. Um, anyway, yeah, and then the drummer, Roger Taylor, he's got an art, he's got a, what has he got? He's got a mechanical engineering degree, and then I think Freddie Mercury had an art degree. So they're all, they all have college educations, very educated band. Anyway, they did the theme song for the movie Flash Gordon back in 1980, which is frankly terrible. It's not a good movie. But the theme song, on the other hand, is better than the movie. And so I don't know if you know who Flash Gordon is. He's like sci-fi from like back in I think like the 1930s. Um, and so there's this terrible, terrible, well, so bad it's good Flash Gordon movie. So I must share the first part of the theme music. Let's see, after I stop recording here, because I don't want YouTube to say, hey, there's a copyright claim. So let's recording. All right, so now that we've heard Queen going flash, right, we see that when you get to the so-called tip of the red giant branch, you've reached the point at which helium fusion begins explosively in the core. We get runaway helium burning, the degenerate helium core explodes within the star, and we have the helium flash. Exactly. Yes, yes. Glorious. So normally a computer simulation of a star's evolution runs much faster than the actual evolution of the star itself. But things evolve so rapidly during the helium flash, that it actually goes the other direction. it would take much longer to simulate this than it actually occurs in the actual star. So some years ago, I read it'd be better now because we got faster computers, but it was something like to simulate 1 second of the helium flash, the computer would take like 1,000 years or something like that. So we actually can't follow the helium flash computationally unless something's happened in the interim that I haven't heard about. Um, but you can do back of the envelope hand calculations and show that it would be over in a couple of minutes. But the core becomes spectacularly luminous during the helium flash. For at the peak of it, the sun's core's luminosity will be comparable to like the combined output of all the stars in the universe put together for a brief moment, right? That's the power, right? So it's very brief. It's not the energy, power energy is power times time kind of thing, but it's a spectacular explosion within the core. But it turns out the outer layers are able to contain it. And remember that radiative diffusion takes a long time to get energy generated into the core out to the surface. So in other words, if you are watching the star from the outside during the helium flash, you wouldn't be able to tell what was happening. You wouldn't know. Because that stuff, that energy takes a long time to get to the surface. But nevertheless, you would not immediately, but you would see the effect of the end of the helium flash because once the temperature reaches something like 1 billion Kelvin, the electrons are so energetic that they're at energies that ordinary classical thermal physics could account for. They stop being degenerate. The core, we say that the degeneracy in the core is lifted, so to speak, and it expands and cools down and settles into stable helium burning within the core. And so now we've got a kind of second, if you will, main sequence phase, if you like, except that it's a helium burning main sequence, if you like. And it's not along the main sequence anymore. It's in a small region of the HR diagram. But in other words, you get something similar to what you would have if you had a star that was made of nothing but helium and it had core helium fusion going inside of it, except the star isn't nothing but helium. You get a stable helium burning core surrounded by a hydrogen burning shell. That's still going on, surrounded by a non-burning hydrogen envelope. Even though we've got two sources of energy now, the star is less luminous. It's producing less total nuclear power than it was as a red giant because the core, the helium burning core, has expanded and cooled, and the region of the hydrogen burning shell is now at a lower temperature than it was as a red giant. And so the combined luminosity of the helium burning core and the hydrogen burning shell for the sun will be about 50 times the sun's present luminosity. So pretty impressive still. But how luminous did I say it roughly will get at the peak, at the tip of the red giant branch when the sun is a red giant? Why, its luminosity right before we get the helium flash reaches about what, roughly speaking? Do you remember what I said? What? No, no. I don't mean during the flash. I mean, just as it expands and it's a red giant and all that stuff. The surface luminosity it peaks at about something like 2,000 times its present luminosity, right? So a horizontal giant, when the sun's a horizontal branch star, it'll be like 50 times its current luminosity. Impressive, but a lot less than 2,000 times its luminosity. So it's much smaller and dimmer than it was as a red giant. Impressive, but not as impressive as the red giant phase was. Why do we call it the horizontal branch? Because horizontal branch stars, if you plot the V filter magnitude on the HR diagram, use that as the axis, they lie along a nearly horizontal little segment of the HR diagram. It's kind of like a horizontal helium main sequence, if you will. And so that's, as a result, they're called horizontal branch stars because astronomers can't help themselves giving things names that make it hard to understand exactly what it represents. So as astrophysicists, we know it's because it's on a horizontal portion of the HR diagram. The book I use in Astronomy 111 gives it a more descriptive name, which I frankly think is better. It calls it a helium core fusion star. What would be easier for you to remember what's going on if you heard the name of the star? It's a helium core fusion star. Huh, I wonder what's happening in that star versus it's a horizontal branch star. Huh, I wonder what's happening in that star. Well, let me look it up. Oh, that's when it's core helium fusion, right? So if you want to think of it as a helium core fusion star, go for it. Be the next generation that fixes this stupid name, all right? But the official name is horizontal branch star. So that's the next stage of the sun's life after the red giant branch ends. After it gets to the tip of the red giant branch, it experiences a brief helium core flash. And then it quickly moves on to the so-called horizontal branch. You see it's like 10 times its current radius at that point. So show you some photographs of some horizontal branch stars. Where's a good place to find them? Well, you can find them in the galactic disk, but there's another place where, wow, you see lots of them. So remember that our sun is part of our Milky Way galaxy. Here's like a schematic side view in the plane of the disk. So here's the disk of the galaxy. I don't remember if I said it, maybe you know it. How wide is the disk of our galaxy in light years, roughly? About 100,000 or so, about 100,000. Making mental models is very helpful to me. I think that we should do that sort of thing. So suppose that the astronomical unit, the distance from the Earth to the sun, was represented by 2 millimeters, right? Two of the smallest divisions on this meter stick. So the sun is 2 millimeters away from us. How big is the disk of our galaxy in that same scale model, to that same scale? The answer is the size of the actual planet Earth is the size of the disk of our galaxy if the astronomical unit is 2 millimeters. This is why, for example, people tend to like say solar system, galaxy, yeah, it's all no, right? No, the solar system and the galaxy are such vastly different scales. And our star is one of several 100 billion stars in our galaxy. Solar system and Milky Way / galaxy, totally different concepts, right? Never confuse those things. Meanwhile, there is the halo of the galaxy above and below the galactic disk. Of course, there's no up or down, right? But whatever in space. But if you want to above and below, there's a spherical galactic halo composed of both field stars and globular clusters. A globular cluster is around 7,500 light years across or so, can contain up to like 1 million stars. They're all very old. They seem to have been born before our galaxy had fully formed yet. There aren't any globular clusters being formed today, as far as we know. I think there's some candidates for maybe, but in any case, essentially they were formed long ago. They're all old, billions of years old. In fact, they're around, they can end like 7 billion years to like 11 billion years old or something like that. Wait, how long will the sun spend on the main sequence total? About 10 billion years, right? So globular clusters are comparable in age to the sun's lifetime on the main sequence, as a matter of fact. And that means when we look at globular clusters, we can see low mass stars comparable to the sun's mass or thereabouts that have become red giants and horizontal branch stars. And so here's a photo of the globular cluster M10. In other words, it's number 10 on Charles Messier's list of things that are not comets. It's a globular cluster. And here's a zoom in on part of it. Red giants. There's lots of red giants in a globular cluster. In fact, they're the most luminous stars in it because are there going to be any O and B main sequence stars, the most massive main sequence stars? There's not. Why? They blew up a long time ago. They blew up good a long time ago because they only live a few million years. And a million years is a thousandth of a billion years, right? So there's no O and B type star. They blew up a long time ago. There's neutron stars and black holes. There used to be O and B stars in them, but no O and B stars anymore. So the most luminous stars in a globular cluster are going to be low mass red giants. Look, it's low mass red giants. And here's some horizontal branch stars in there as well. So when we make the HR diagram of a globular cluster, as we'll see shortly, you see the red giant branch and you see the horizontal branch very nicely in them because there's plenty of examples of both types of stars in there. So will the helium burning in the core last forever? No, because is there an infinite amount of helium in the core? No, it's going to eventually run out of helium in the core. And then we get a sort of, in a way, repeat of what happened when it ran out of hydrogen in the core. So helium burning turns the core into what element primarily? Carbon. It's mostly carbon, but there's also some oxygen and other stuff too, but it's mostly carbon with some oxygen. And when the helium fusion is done, it's not hot enough to fuse carbon into anything because that takes about 600 million Kelvin. And the sun's core will never get to that point. So the sun's core will remain being made primarily of carbon and in fact will become the final remnant of the sun. The sun's burnt out carbon oxygen core will eventually become the sun's white dwarf remnant. That's what a white dwarf is. It's the burnt out carbon core of a low mass star like the sun. But we got to get there. Well, just like the helium core contracted, heated up, and made a shell of hydrogen fusion surrounding it, and that went faster than the hydrogen fusion in the core ever did because it's much hotter than the core ever was when it was burning hydrogen into helium. And the sun swells up into a red giant. It's going to be a red giant again now. The carbon core is going to contract, heat up, and initiate helium fusion in a shell surrounding it. But there's also hydrogen fusion in a shell surrounding it. And so now we get a second red giant phase where the energy released by the furious hydrogen fusing shell and helium fusing shell causes the sun to swell up again. And because we're astronomers, it has to have a ridiculous name. The second red giant phase of the sun, we will say it's an asymptotic giant branch star. Now, say that 10 times real fast, and you quickly decide, I'm going to say AGB star instead. So if you hear astronomers say AGB, you know what they mean is asymptotic giant branch. Why does it have such a weird name? Okay, well, in math, if one curve approaches another one, we say that it approaches that curve asymptotically, right? And so the evolutionary track of the star asymptotically approaches the red giant branch. So, of course, we'll call it an asymptotic giant branch star. Why, there's nothing asinine about that, right? It's an asymptotic giant branch star. Yes, of course. The Astronomy 111 textbook calls it a double shell fusion red giant, which you could argue is a bit more descriptive than asymptotic giant branch star. Maybe you all can go forward and spread the good news that we should be calling these things double shell fusion red giants. But unless you're successful, everybody's going to say, oh, you mean an asymptotic giant branch star? Okay, so that's the official name. asymptotic giant branch star, where you've got a non-burning degenerate carbon ash core surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell. Once again, this is a tiny, tiny, the textbook is the Astronomy 101 textbook, not our textbook. No, it's asymptotic giant branch star in ours, because it's written by astronomers. Well, so is my other textbook too, but you know, if you're writing for people who are supposed to be future astronomers, why you gotta get them to say asymptotic giant branch star, AGB star. Anyway, again, it's this tiny, 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 tiny little region in the center of the star, like Earth size. When the sun's an AGB star, right, it's even bigger and more luminous than it was as a red giant. For the first time, I've seen about like 5,000 times its present luminosity at the maximum when it's an AGB star, when it's a double shell fusion red giant. So a low mass star like the sun is a red giant twice, essentially. There's two red giant phases. Only we really only call the first one the red giant phase, and the second one's the asymptotic giant branch phase. But it's really a red giant again, right? It would look like a red giant again. But this is the beginning of the end. This is the sun is doomed at this point because of the fact, actually, I'm going to skip this part right here and get to here, because of the fact that it turns out that helium fusing shell is unstable because of its thinness, it turns out. So here's the structure of an old low mass star. We'll get back to the 5 solar mass star next time. Here's an old low mass star like the sun. So as an AGB star, right before we said as a red giant, the first time it gets like half the current distance to Earth. The sun as an AGB star is getting to be its size is comparable to 2 AU across, like it's almost at Earth's orbit. Now, Earth, so there will also be a strong stellar wind when the sun is a red giant and when it's an AGB star, because it's so distended, gravity is very weak in the outer layers, and so pressure tends to blow off a lot of mass from the outer layers during those phases. And that means the sun's gravity will be weakening, and that means that the Earth will be backing away from the sun during these periods. So in other words, Earth will not be swallowed by the sun. It'll have backed away before that could happen. But nevertheless, there in the middle, we've got the carbon-oxygen core. We've got a helium fusion shell. Notice it's saying a dormant hydrogen fusing shell. Well, actually, it's a back and forth. They go back and forth. So initially, an AGV star has an inert CO core surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell. Eventually, the hydrogen-burning shell becomes dormant due to expansion and cooling of the layers around the core. All this energy from the helium fusion shell is causing the region nearby to expand and cool, and that'll switch off the hydrogen burning shell. As helium burning depletes fuel in the helium burning shell, this is again according to stellar calculations, sophisticated computer models, helium burning slows to a halt. Now the helium burning shell is dormant. But now the pressure holding up the dormant hydrogen burning shell decreases. And so that contracts, heats up, and starts burning hydrogen again. Okay, so we're cycling here. Newly created helium rains down on the helium burning shell. The extra mass and gravity causes it to contract and heat up as it gains mass. And when the temperature gets high enough, helium burning reignites explosively in not a helium core, but a helium shell. Flash! Yes. You get a helium shell flash, and it turns out it's because it's very thin, and as a result, when it starts fusing, because it's so thin, pressure can't make it expand and cool down, and so you get another thermal runaway within the helium shell. So you get a helium shell flash, and the star's luminosity jumps in what we call a thermal pulse as a result of that. And so this cycle keeps going, and you get a whole series of helium shell flashes. So now we get to say, so here is, and by the way, yeah, the reason I say video 745-806 is that I think if I took it out of these and put it back in, There's a video from Crash Course Astronomy that goes through all of this. And I key into like, well, where in the video is this talked about so that you can look at the nice Crash Course Astronomy video later. Because, you know, he has special effects that I can't do, right? He's got a production team behind him that's good at lighting. Anyway, here's for a 0.7 solar mass. I don't know why they picked 0.7 solar mass, but computer model of helium cell flashes and a 0.7 solar mass star. Notice the time scales here. So here's one, and then, so there's a helium shell flash. And then 313,000 years later, there's another helium cell flash. And then 295,000 years later is another helium cell flash. And 251,000 years later is another helium cell flash. And 231,000 years later, another helium cell flash. Yeah, I tried to say flash. Well, there's another helium cell flash. Notice it's getting closer and closer together. I mean, it's hundreds of thousands of years, but still, it's getting closer and closer together. And the star's luminosity keeps pulsing, right? Up and up and up. Every time you get a helium shell flash and thermal pulse, you get extra pressure in the outer layers, which is starting to lift them off. And the final one pushes the final remnants of the envelope off the star. And we get the ejection of a lovely planetary nebula, like the Ring Nebula, for example. I believe that's M57 on the list of things that are not comets, yes. So the sun, we now think it's been just like debatable whether the sun's massive enough to make a visible planetary nebula, and the answer seems to be yes. So you get this, we'll see pictures next time, a lovely shroud of material, the last remnants of the envelope of the star, surrounding the burnt out carbon core, which will, because it used to be the core of a star, be very hot initially and stay that way for billions of years, where the surface temperature is like 50,000, 100,000 or so Kelvin, producing enough ultraviolet light to ionize the gas surrounding it and do something similar to what happens with an H2 region. In other words, recombination causes the material to glow with spectral lines. And so what happens is that the burnt out core rapidly moves down into the white dwarf region of the HR diagram. And that's the end of the story for the sun, or stars similar to it. The burnt out carbon oxygen core is left behind as a white dwarf. Meanwhile, the planetary nebula dissipates in a few tens of thousands of years into the surrounding interstellar medium and returns some of the material that was made in the core into the surrounding interstellar medium to be incorporated into future generations of stars. Because while we said that stars are not well mixed, there is a period when the sun's a red giant where you get what's called a dredge up, where convection reaches down into the core and stirs material up into the surface layers. And so we get, for example, what we call carbon stars, which are unusually rich in carbon in their atmospheres. Where did it come from? Helium fusion in the core produces, or in a shell surrounding it, produces carbon that can be dredged up into the outer layer, similar to how you can dredge the bottom of a riverbed and get all the crap on the bottom, the sediment on the bottom, into the surface water. Stars can do something similar and change their surface composition. So these outer layers have nuclear process material from the core mixed into them. It dissipates into the surrounding interstellar medium to be incorporated into future generations of stars. Some of the atoms in your body used to be in planetary nebulae, which is kind of like the planetary nebula pointing into the interstellar medium surrounding, right? So turns out we are connected to the stars, right? Pretty cool. Preaching to the choir here, but pretty cool. All right, time to go. Yes.
Star. A lot more matches.
No, that's not a particular issue here. No, because so higher mass stars actually go through the instability strip on the HR diagram multiple times and go through periods where there are pulsating variables. But this bit isn't really part of that. This is a separate process from that. So that's a different thing. It's not because of the interplay of the fusion in the shells. It's it turns out that it's related to, and we'll say something about this when we talk about white dwarfs. Uh, there's a whole chapter in your book that we don't have time to cover about it, but ionization zones can produce a situation where they can temporarily kind of trap heat within the star, and it turns it into essentially like a heat engine. It actually kind of acts a bit like a piston engine. And so you get a situation where the star is pulsating, but it's on a much faster time scale than what we're talking about here. Yeah, not hundreds of thousands of years, but days, weeks, that kind of time scale. Yeah, it's an interplay of the opacity within their ionization zones being such that, unlike the normal situation where if you compress the material, it would become more transparent and make it easier for heat to escape under the right conditions. Compressing it can cause it to become more opaque and dam up energy behind it. And so there's a lot more to it, but that's essentially what's coming. So that's the difference.
At the science fair, with the angular momentum conservation there. And I got to do both of that.
Oh, cool. Nice.
And
So let's see. Yeah. So both means both pulling in and then with a gyroscope, you mean?
Yes.
Oh, yeah. Uh-huh. Yep. Yep. So you conserved angular momentum properties. Congratulations. Yes.
Ice skater example that you put to us.
Yeah. The classic ice skater example.
Strong.
Yep. Absolutely. Yeah, when we talk about neutron stars, I'll have to do that here too. Yeah, just have to, yep. Yep. Mhm.
Asking about our set.
Yes. Mhm. Okay, what am I doing? I am stopping me.
It's slightly flat and it didn't spin us there.
Oh, really? Oh, okay. Huh.
But the one with the dumbbells, it's been very fast.